We'll first discuss some very basic magnetic principles. What happens when current flows in a conductor, what is flux and how is it generated, how is a force produced that moves a conductor, and finally, what happens when a wire or a conductor is moving in a flux field. Everyone has had experiences with magnets. Attraction and repulsion are two basic principles of magnets. Magnets have north and south poles. Unlike poles attract each other while like poles repel. Magnetic flux refers to the flow of lines of force between two poles, and flux lines of force always flow from the north magnetic pole to the south pole. If an electric current flows through a conductor, a magnetic field will surround the conductor. When the conductor is wound into turns, the magnetic fields are superimposed, and this is known as a electromagnet. The result of the magnetic field is similar to a bar magnet where there's a north pole and a south pole. As with a bar magnet, the electromagnetic field flows from the north pole to the south pole. Increasing the number of turns in the coil increases the strength of the magnetic field. This is because each turn of the coil adds to the overall magnetic strength. Increasing the amperage or current flowing through the coil increases the magnetic strength. And finally, the strength of the magnetic field can be increased when the coil is wrapped around an iron core. So there's three ways to increase magnetic strength of an electromagnet: increasing number of coils, more current, and wrapping around an iron core. And here's another example of a magnetic field flowing from the North Pole to the South Pole through an air gap. So we said an electric current flows through a conductor, a magnetic field will rotate around it. Well, the direction of the rotation of the magnetic field can be determined using the right hand grip rule by pointing the thumb of the right hand in the direction of the current flow and curling your fingers around the conductor. Your fingers will point in the direction of rotation. And changing the direction of current flow will change the direction of the rotating magnetic field. When a conductor carrying current is placed in a magnetic field, a force will be applied to the conductor. The conductor rotating flux field and the stationary flux field interact. This interaction produces a force that is perpendicular to the lines of force. It's important to note that the direction of the current flowing through the conductor and the direction of the magnetic field determine the direction of the force. Here, above the conductor, the rotating field is in the same direction as the main field, so it strengthens the main field. But below the conductor, the rotating field is in the opposite direction of the main field, and so that weakens the main field. The result is a force is applied on that conductor in the direction of the weakened field or downward. You can think of the lines of force like rubber bands. They're always trying to shorten themselves. A coil has two sides. Current flows in one side and out the other. When placed in a magnetic field, there'll be a downward force applied to one side of the coil and an upward force applied to the other side. So that's it. The coil starts to spin. It's perpendicular forces that cause the coil to rotate and not magnetic pole and attraction and repulsion. Now let's see what happens when a conductor travels in a flux field. Faraday's law states that when a conductor is exposed to a changing magnetic field, a voltage is induced into the conductor. The voltage is proportional to how fast it is moving and the flux strength. The voltage will only be induced in the conductor if it's cutting across lines of force. The induced voltage is called counter electromotive force. If a conductor is moving through a magnetic flux field and does not cut lines of force, no voltage is induced into the conductor. In this example, the conductor is moving parallel with the magnetic lines of force and not cutting lines of force. Counter EMF as it relates to speed control and torque output is very important. In this slide, we see the counter EMF developed in the conductor opposes the voltage that's applied to the conductor. When voltage is applied to a motor, rotation occurs. The conductor is rotating in a flux field. Therefore, there's a counter EMF that's developed which opposes the applied voltage. The difference in the applied voltage and the counter EMF is the voltage used to drive current in the motor.